I am now testing this amplifier with the BUK 75150 on the interferometer. So this has a gain of 6 decibels and it is 50 ohms on the input as well as on the output because of noiseless feedback. Of course, it is 50 ohms on the input only if the output is connected to a 50 ohm load. First step is to calibrate the system. Here is the SDR IP, and I click on the carrier on 10 megahertz. Like this. And I have set the S-meter graph to show 0. It just showed error, but now it shows 0.01. And then I add this signal 10 kilohertz down, and I have to click on it. And fine-tune to get it into the filter. I have adjusted the level on the signal generator until I read here -70. So this is my reference to compare the noise floor to. This signal 10 kilohertz away is 70 decibels below the carrier. On the linear screen I have it here, and I read the level -70.06. This is good enough. And I switch off the generator like that. And the bandwidth is 1 kilohertz, and the noise floor I see is -155. That is -185 dBc per hertz, and that seems to be good. But when looking at the spectrum, there is a noise hump here, 170 kilohertz up. There is not a similar noise hump here, 170 kilohertz down. And there is a smaller noise hump here. And of course there is also some leakage of shortwave stations because I have got the lid on. But this is the sign of a design error. The supply voltage comes in here through a feed-through capacitor, goes through a resistor and a small capacitor to ground, probably 0.1 microfarad, and from that point a diode for protection purposes to an electrolytic capacitor, 470 microfarad. And then there is 10 kilo ohm and a Zener diode and a big tantalum electrolytic to provide the bias voltage for the gate. And then an inductor, 10 microhenry, and another fairly small capacitor to ground. One problem is that this inductor and this capacitor form a resonance, and there is no resistor across the inductor to attenuate it. So as a first step I just bypass that inductor. So I just soldered a wire across it, and then the screen here becomes quite different. The noise hump here is gone. This one is still there, but not so strong. And I can see the leakage of HF signals better. The noise floor, I was -155.11 before. minus 155.2. That's not a significant difference. But there were really significant changes out in this high frequency region. I will try some further modifications. I'm looking now at the separation of 1 kilohertz, and I have some problem with microphonic like that. It is connectors, it's the 3 dB attenuator mainly. But I look at the noise floor between these noise bursts, and it shows minus 152. And then I add this 470 microfarad electrolytic in parallel with the small capacitor to decouple the drain voltage at low frequencies better for the MOS-FET. Now that electrolytic capacitor is in place, and I look at the noise floor, it was 152 before, but this time it is lower. I have to hit the point when the connector noise is not present, minus 152.9. But it goes lower occasionally. So I will try to find what connector to work with before continuing with this. Now it looks stable. Well, not if I bang on the board like that, but yeah. Minus 154.5. And I will remove that big electrolytic to see whether that was really doing this. Now the electrolytic is disconnected, and I check, oops, here. It's still minus 154. So it seems it doesn't make any improvement. And that's not very unexpected. I have rearranged the bias voltage for the MOS-FET. Previously I had only this 10 kilo ohm resistor, the Zener diode, and one tantalum capacitor to ground. Now I added 100 kilo ohms from that bias point I had before, and then another 10 microfarad tantalum capacitor. So the bias should be better decoupled from the noise coming from the Zener. This makes a very small difference. It makes, at the separation of 5 kilohertz, it improves by half a decibel. And I have not checked what happens at closer range, but this is obviously something that is not bad, so I adopt it. I have now calibrated at a separation of 200 kilohertz and switch off that extra signal so I can now read the noise floor. In 1 kilohertz I find 158.5. And then I bring up a lot of attenuation, so the system after the combiner looks into the attenuator, and what I will see is the system noise floor. And that comes at minus 162.2 dBm. And of course it says dBm on the scale, but I have calibrated, so this means dBc, decibels with respect to the carrier, and in a bandwidth of 1 kilohertz. Here is the separation 50 kilohertz, and I had to recalibrate because the gain is about 1.5 dB higher. That is because I have this band pass filter in front of the low noise amplifier. So I switch off calibration signal, and here is the noise floor at 50 kilohertz. Minus 158. Well, once more. Minus 157.9. That was not okay because I was outside. (157.9) with a high attenuation here. I now see minus 162.6, and here is 10 kilohertz. I checked calibration and I was reading 155.57, and with the attenuator in I see 162.6. Well, I will continue to make these measurements at various separations and also different bandwidth, and plot on the log scale to see how this looks. I will check the power level by connecting the spectrum analyzer to see the same signal that I have been feeding into the device under test. So here is what we see. The level is 19.5 dBm. So that's the carrier. Below 1 kilohertz separation, I don't see the flicker noise because there is other forms of modulation. I have tried to find out where this comes from, but I have not been successful so far. Maybe it is microphonic. I switch off the other instruments. And this made a change of the amplitude because the spectrum analyzer was loading a little bit. So I restore balance. And then look here. But the modulation is still there. And I have no idea where it comes from. Looks like computering because this is an on-off thing. Well, now I have ugly modulation sidebands. But if I switch off this generator, they go down very much. Now the balancing changes. This affects the amplitude, and I don't know why. It's not that I connect or disconnect the cable. It has to do with the mains somehow. So I have to verify. Well, I have to do the balancing properly. And now it looks much better. I have switched off the computer for the SDR-IP because that caused a lot of ugly sidebands also. And I have this mechanical stability problem, as you can see. But I will try to estimate the noise close to the carrier. First I have to go through all the BNC connectors because one of them, or maybe a few, are not good at this moment. I have cleaned all the BNC connectors in isopropylic alcohol and there are still stability problems now and then, but much less. And it's interesting, this is noise at a fairly high offset. And when I tap on the table, you can see there is a lot. Anyway, I will try to measure the flicker noise in this gap, or maybe very close to the carrier also. This is a frequency separation of 10 Hz in a bandwidth of 5 Hz. And I have some glitches. Maybe I didn't configure things quite cleverly enough, but the level I see is minus 151.1. And here is the result. The BUK 75150 amplifier here is about 20 decibels better than the AMC 147 in terms of flicker noise. It can manage much more power, so the flat noise floor is also much lower. The SPF 5043 is really very noisy, and I don't know what to say about it. Most probably don't use it. Now I'm running Linrad in coherent mode. Coherent mode 2 means that I select what comes within the narrow filter here, which is the carrier, and use that as a reference to detect I and Q from the entire spectrum. And that is sent over the network and received here. And here we can see something interesting. All the spurs at the center, they are green, and they together make a level of 125, while the red, which is noise mostly, is 45 dB weaker. So the green is far above the red. I can expand the scale, which might make it easier to see. The carrier at the center, that is of course the reference, so that is AM. But if I click a little bit, I can reduce the bandwidth and click a little bit on the side. And it's clear that it is much more AM than phase modulation, these spurs. I can allow Linrad to optimize. And the strongest signal is this one, so I can of course make bandwidth much narrower, so I can read the phase angle between I and Q for this peak, and it comes at 164 degrees, and I can click on another peak, this one. Sorry, I have to click in the waterfall. And that comes at 170. Well, it doesn't work so well because when I move I get spurs, bursts, but something like this. And I have set the phase for minimum This is the phase control. So I know when setting 0 here, the green track is amplitude modulation and the red is phase modulation. At an offset of 2 kHz, you can see here I have a big separation between red and green. I have set for adaptive polarization. Well, with a very short time constant, I make it a little bit longer. Oh, not so long. Something like that. This means that the modulation is AM as well as phase. It's the same as in the AMC 147. The close range noise is amplitude noise and phase noise, and they are phase shifted by 90 degrees. This is at 25 kilohertz, and I combine the AM and phase modulation at 45 degrees, and then I see they are well correlated. If I make it like that, then I can see that the AM component and the phase component are equally strong. So, and I go close to the signal, and it's the same here. So phase modulation and AM modulation have the same level at wide separations, well, at separations above 5 kilohertz, but very close because of the spurs. There is a big difference between the level of phase and AM. Now the waterfall shows close range AM noise, and I shift 90 degrees. And now the waterfall shows close range phase noise. And at the very center we are within the narrow filter that selects the phase for the reference, so disregard this central region. But there is obviously some phase modulation with a frequency of what could it be? It is well below 50 Hertz, because here is 100 Hertz, 50 Hertz. It's maybe 8 Hertz or something. I have no idea from where that comes. Maybe vibrations from a fan or something. Because we have microphonic system. I bang on it a little bit. And this is what it looks like. And when looking for AM, banging the same way, it seems to be much stronger here. So the microphonic thing affects AM modulation mainly. It's obvious it would be possible to fix these modulation sidebands. But I'm not going to try to do that, because I'm interested in the limits that could be obtained. I'm not really trying to obtain them in full. So here is the AM component, and again here is the phase component. I changed the frequency span a little bit. And I can go 45 degrees between. So it is possible to provide very good results with this transistor, although I'm not actually doing that at close separations with this setup.